Hello everyone. Thanks ANRF and IIT Mandi for this initiative and opportunity to present our research. On behalf of MS Regist Lab, we will be presenting the work done under ANRF SERB sponsored project that investigates the impact of climate change on the lifetime vulnerability and resilience of aging highway bridges. Bridges are one of the most critical lifeline structures, serving as a vital links in transportation networks. They connect communities, support economic activities, and require significant capital investment. Therefore, ensuring their safety and functionality is essential for uninterrupted transportation and societal resilience. Throughout their service life, bridges are continuously exposed to environmental stressors such as corrosion, flooding, and scour, which progressively deteriorate critical components and reduce structural capacity. Moreover, many existing bridges were designed using antiquated design standards, making them more vulnerable to natural hazards, including earthquakes. Therefore, assessing their lifetime vulnerability is essential for ensuring long-term safety and resilience.
India's aging bridge infrastructure demands timely maintenance and rehabilitation. Over 200 bridges are older than 75 years and 147 are critically distressed. Flood and scour account for over 51% of bridge failures, while earthquake contribute nearly 27%. This underscores the need for lifetime vulnerability assessment and rehabilitation planning. Now, these images show some major bridge failures caused by natural hazards across the world. Most of these failures are associated with earthquakes, floods, and scour, often acting on already deteriorated bridge systems. Climate change further accelerates bridge deterioration by increasing corrosion and intensifying floods and scour. Consequently, aging bridges become more vulnerable over their service life. To account for these future changes, this study incorporates CMIP6 SSP climate scenarios to assess their impact on bridge deterioration and lifetime vulnerability. Now, higher temperature accelerate chloride-induced corrosion, causing cracking, concrete spalling, and reinforcement loss. These deterioration mechanisms reduce bridge strength and ductility, making them more susceptible to severe earthquake damage. By incorporating climate correction factors, the average corrosion initiation time reduced from 31 years to 22 years, demonstrating significantly accelerated deterioration under future climate conditions. After corrosion initiation, the corrosion rate increases progressively under changing climate condition, leading to greater reinforcement area loss and continuous degradation of both steel and concrete properties. Consequently, the bridge experiences a substantial reduction in its load carrying capacity and seismic performance.
Climate change not only accelerates corrosion but alters the hydrological cycle by increasing extreme precipitation and flood intensity. These higher river discharges result in deeper foundation score, reducing foundation stability and causing larger deformations. Consequently, riverine bridges become significantly more vulnerable to structural damage and failure during extreme events. Score can be evaluated using two approaches: as a time-dependent process over the bridge service life or under an extreme flood event. In this study, the time-dependent score depth was estimated using historical discharge data, while the effect of climate change was incorporated through future discharge projections for 100-year design flood. As shown in figure, increasing river discharge under future climate scenarios result in significantly greater score depths, making bridge foundations more vulnerable. Till now, we have seen how climate change accelerates corrosion deterioration and leads to deeper foundation score. To evaluate the combined impact of these climate change-induced hazards on bridge performance, we have developed a high-fidelity finite element model of a typical highway bridge in OpenSeas. The developed numerical model was validated against experimental studies, providing confidence in simulated structural responses.
After developing the numerical model, we investigated the effect of climate change accelerated corrosion on the service load reliability of an RC bridge in Gujarat, India. The result shows that the climate change significantly increases the impact of corrosion, reducing the bridge shear capacity. Consequently, the bridge reaches an unfit for service condition about 18 years earlier, highlighting the importance of accounting for climate change in durability assessments. Next, we investigated the combined effect of climate change accelerated corrosion and earthquake on the seismic vulnerability of aging bridges with the help of seismic fragility curves. The result shows that corrosion significantly increases the bridge seismic vulnerability, and climate change further amplifies this effect, with the highest vulnerability under the SSP5 8.5 scenario. Consequently, the bridge experiences greater functionality loss and lower seismic resilience after earthquake. Next, we investigated the impact of climate change induced score on the seismic vulnerability of riverine bridges. The result shows that the seismic vulnerability increases significantly under future climate scenarios. Compared to the historical condition, the bridge exhibits a higher probability of failure under the both SSP2 4.5 and SSP5 8.5, with the highest vulnerability under SSP5 8.5 scenario. Likewise, the increased core depth due to climate change significantly reduces seismic resilience of the bridge. Finally, we investigated the combined impact of climate change-accelerated corrosion, scour, and earthquakes on the seismic vulnerability of bridge systems. Unlike previous studies that considered these hazards independently, this work developed time-dependent multi-hazard fragility and resilience curve by incorporating the coupled effect of corrosion and scour under changing climate conditions. The result shows that the bridge failure probability increases progressively over the service life as corrosion and scour intensify, resulting in greater post-earthquake functionality loss and a significant reduction in seismic resilience. So far, we have seen that climate change accelerates corrosion and scour, therefore increasing the seismic vulnerability of aging bridges. However, mitigation is equally important. While seismic retrofitting is an effective solution, its performance depends on the retrofit configuration and intervention timing. Optimizing both is therefore essential to maximize safety, extend the service life, and improve sustainability. Therefore, we next investigated suitable retrofit strategies to mitigate these adverse effects. First, we evaluated the effectiveness of FRP jacketing in improving service load reliability. The result shows that strengthening the bridge girder with FRP delays deterioration and extended service life. FRP jacketing was then applied to the bridge pier, thereby reducing its seismic fragility. Finally, RIPRAP was adopted to mitigate climate change-induced score, improving foundation stability and later load resistance while reducing the seismic vulnerability of the bridge. Finally, we evaluated the effectiveness of these retrofit strategies in terms of seismic risk and resilience. The result shows that timely FRP retrofitting reduces seismic risk by enhancing the bridge structural capacity while improves foundation stability and seismic resilience under climate change. Overall, both strategies effectively mitigate climate change impacts by reducing the bridge vulnerability and risk while enhancing the resilience.
The outcome of this research have been published in several reputed journals and international conferences in the field of structural and earthquake engineering. Finally, we would like to express our sincere gratitude to the ANRF for their generous financial support which made this research possible.